All right. Repeating what I just said, I forgot I hadn't turned on the recorder yet. The Vice President for Instructional Services had directed that we read this memorandum to the students, and basically it's saying that if you have not completed your financial obligations to the college, please do so as soon as possible. If your name's not on the official roll, which means you've completed all of that, then we're supposed to send you to the business or financial aid office to check on your obligations, to get it underway, and it says that we, the faculty, are not to allow you back in the class until your name appears on the official roll. As I said, I think all 4 of you who have been coming are on the official roll, so I don't think this pertains to you, but I had to read it. So, thanks for your cooperation. Now, the next thing is not, I sure hope it's not going to be an issue, okay? Next Tuesday, I've got a different doctor's appointment. This is one for my hematologist, and that's going to be at 9 o'clock in the morning. And if he's not through with me, by the time this class is going to start, I'm going to walk out. So there's no chance, I don't think, knock on wood, that that there'll be any problem with getting to this class. I'll miss my first class, but what we've already decided to do with them, and they agreed to it this morning, the ones that were there, is I'm going to have their class at 11 o'clock. None of them had an 11 o'clock class, so they're just going to come in a little later. We'll have class at 11, and that'll get over with at 1:15. So I won't have as much time to do other work in the afternoon, but I'll get done what I can. So that's going to be Tuesday. So don't think there'll be an issue. I'll be here, knock on wood, in plenty of time for class, hopefully. If I'm not, hang still tight, because I'll be here. But I don't see any way I'll be going that way. Because he only sees patients on Tuesday mornings anyway, so I'm not going to be around there later. All right, that's the only things I can think of, except for this. I am behind on grading. That's why you haven't seen your grade show up on Blackboard yet. But this is the good news about having the doctor's appointment. That way, I'm in his office. I usually can't get internet. I can't do anything else, but I take my papers with me. I'll hopefully get caught up on grading. If I can't get on the internet, I still can't put them on Blackboard, but I will get them graded. So, again, knock on wood. I hope that if I can't get them done this weekend, which I'm hoping to do, then we'll, hopefully by then I'll get them done. All right, any questions? Anything we've covered so far?
Can you, on number 11, page 218.
Okay. Let me get something to mark my place here. Number 11 on 218. Got it.
Can we work this out?
I'll see if I can. All right. This is page 218. Let me get my pen set up. Goodness gracious. Page 218. All right. This is section or problem set 8.4, 8.3. And it's number 11, you said?
Yes, sir.
All right. A 30.0 gram bullet. 30.0 grams. What's that a measure of? What do we measure in grams? What quantity in nature?
Kilograms, weight.
No, not weight. Weight is in newtons. What do grams and kilograms measure? Meters or distances? I think you're thinking the right thing. You're thinking M, but as a parameter, M doesn't stand for meter. For a unit, it stands for meters. What does M stand for as a parameter? As a symbol. Mass. That's your mass. Okay? Now, before we go too much further in it, I do want to read the rest of the problem. Yeah, we're going to have to do this. Grams is not the SI unit for mass, though. You said what that was. What? Not grams, but kilograms. So what we have to do is convert this mass to kilograms. Did something just fall? Huh? Oh, man.
The cord behind you, baby.
What?
The cord behind you.
Oh! I see. This got all wrapped around the chair and came out. There's no way to fix it. Both plugs have screws and these to screw into. So sorry about that. It came back. Thank you. All right. So what I want to do here is erase. This isn't. Okay. I'm going to put my mass on the other side. Okay. The mass is 30 grams. But we need to convert this to kilograms. Now, you don't have to do this conversion. I'm just going to do it this way just to remind you of how you convert normal things. One way you could do this is just move your decimal. You just got to remember which way to move it. This way, you don't have to remember which way to move it as long as you do this right. Now, this is for a conversion factor. And notice I put two blanks here. One blank's for numbers and one's for units, just like number, unit, number, unit, number, unit. Okay? Which do we fill in first, the numbers or the units? The units. Always put the units in their place. So, there's a line here. One goes on top and one on bottom. Which unit goes on top and which on bottom? Between grams and kilograms. Kilograms on top and grams on the bottom. Now you answer the question of the numbers. How many kilograms in a gram or how many grams in a kilogram?
How many grams in a kilogram?
Yeah.
Is it one? Is it one?
No, then they would be the same units. What does kilo stand for? That metric prefix, kilo. Whether you're talking about meters, grams, liters, whatever you're talking about. What does kilo stand for? Okay, we did it last time with joules and kilojoules. What does it stand for? Kilo. Okay, think of this. A meter is about the distance from my tip of my finger to my opposite ear, right? That's 1 meter. 1,000, okay? You said? I can't hear. Speak up. Okay.
That's why I got puzzled. Then I went to millions.
Okay. Okay, I didn't even hear million. Okay. All right. So where does 1,000 go? With which one?
With kilowatts.
Okay, the same thing with watts. But where does 1,000? So we got the units. Now put the numbers in their place. Where does 1,000 go? With the grams or the kilogram? Kilo means 1,000. 1,000 grams is 1 kilogram, right? A kilogram's really big. A gram is really small. So it takes 1,000 of those little grams to make 1 kilogram. Okay, what I was saying about meters, this is 1 meter. 1,000 meters is a kilometer, and that's close to a mile. Not quite a mile, but it's close to it, about 6/10 of a mile. So the 1,000 goes with that. And you put the units in the right place so the grams will cancel out. So if you do 30 divided by 1,000, what do you get? Basically, you can move the decimal 3 places to the left. Say again? 0.0300, because you had 3 significant digits there, you need 3 significant digits there. Those first 2 zeros are not significant. Starting with the 3 and to the right, those are significant. So there's your mass. Okay. 30-gram bullet is 0.0300 kilograms. Okay? We only got the first few words of the problem read so far. Is fired from a gun and possesses 1,750 joules of kinetic energy. So they just told you what it was. Energy, E sub K, is 1,7. Goodness, I can't write tonight. Okay? All right. 1750 joules. Okay? Make sure I read it right. Yeah. 1750 joules. But I don't want to use joules because joules is a big quantity. I want the fundamental quantities. So what's a joule? 1750. What does a joule stand for? What are the basic units? Kilogram. There's more to it. Units are important. They're your friends. Keep up with them. Kilogram. A joule. Okay. Say again. Meter is okay. Kilogram meter. More than that. Okay, per second squared. Now that is a Newton. A kilogram meter per second squared because it's a mass times acceleration. Mass in kilograms, acceleration meters per second squared. But a joule is a Newton meter, so you need another meter there. So it's a kilogram meter squared per second squared. So there's your kinetic energy in joules. Now, a 30 gram bullet, which is 0.0300 kilograms, is fired from a gun and possesses 1750 joules, or kilogram meter squared per second squared, of kinetic energy. Find the velocity. So this is what we're looking for, velocity. Can you think of a formula that relates kinetic energy to mass and velocity? Say again? Okay, which multiplication?
We're going to multiply 1750 joule times 0.0.
Okay. Now let's just look at the units and see if that would make sense. Then you would have kilograms times kilograms. That would be kilograms squared, meter squared per second squared. That doesn't sound like anything close to a unit for velocity. So no, you don't multiply there. Come up with the formula first. A formula that relates kinetic energy, mass, and velocity. You know it. You did it last Tuesday. What formula relates kinetic energy, mass, and velocity? If your book is open to 218, just look across the page at 219. And just above that green box at the bottom of the page, you see max kinetic E sub K, which is kinetic energy. What is that? Say that again. The square one? Is that what you said? It has a square in it. No, not the one with the square root, the one above it. Kinetic energy is? No, that's potential energy. That's underneath E sub P. Underneath E sub K, what do you see? Right next to it. Yeah, 1/2 what? There you have it. E sub K, kinetic energy, is equal to 1/2 mv squared. There's the E sub K, there's the m, and you're looking for the v, all three of them in that formula right there. Okay? Now, you have a couple choices here. You can move your terms around, your elements here in this formula around to try to solve for v, or you could plug in the numbers and then move the numbers around. I don't care which one you do, not too much. It's sort of easier to move the letters around because they're less writing. So what you can do to get rid of the 2 over here, we want to isolate the v, okay? That's why I pointed at it. So let's multiply both sides by 2, okay? And that wipes out the 2 there, right? We want to isolate the v, so let's divide both sides by m. And there we've divided by m. So that gives you v squared is equal to 2 e sub k divided by m. right? Now, you really don't want v squared. You want v. So what do you do now? And this is, you were mentioning it earlier. You said it earlier. Not multiply. How do you undo a square root? I mean, undo a square. I said it. Take a square root. So if you take the square root of both sides, you get v, the square root of v squared is just v, and that's equal to the square root of 2 times e sub k. Well, that's 1750 kilogram meter squared per second squared. That's your e sub k. Okay? Divided by your m. And your m is this one up here, 0.0300 kilograms. Now look at your units. This kilogram cancels that one out. Fantastic. Because we don't need kilograms in your velocity. Okay? And so let's do the division first. 2 times 1750, I think I can almost do that in my head. That's the square root of 3,500. I'll keep my units, meters squared per second squared, divided by 0.0300. You can probably do it quicker on a calculator than I can, but I can do it if you want me to. Move this decimal 2 places that way, move this place 2 decimals in the same direction, and then divide 3 into 3,500, and you get the square root of 1,1,666. Well, let's see how many. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5. One more. Let's just make that last one 7. Okay, we don't need that many significant digits, but that's what you got. And then take the square root of that, and this time I'm going to ask you to do that on your calculator. If you haven't already done it on the calculator, that's going to be something around 300 and some, right?
It's going to be 300.
I'm just guessing, around 300 and some. Do it on your calculator, see what you get. Square root of 116,667. Okay. Now either I'm doing something wrong or the calculator is, or the calculator operator is. I don't know which. Let's see. Okay. Let me look just a second and see if I'm doing it wrong. This is... Say again? Now that sounds more reasonable to me. Okay. Okay. This is 8.3, number 11. Yeah, you say 340 what? 341.5. Okay, you round that to 342 and you got it. So that's approximately equal to 342 meters per second. Because you don't just take the square root of the number, you take the square root of the units as well. It was meter squared per second squared, and that would be that. Oh, okay. It's supposed to be, that's why I did that many digits. Okay. Probably because you can't read my ugly writing and you're making fun of it, and it doesn't hurt me too bad. Okay. Okay. That looks maybe a little bit better. All right. About 342 meters per second, which is, I think, pretty reasonable for a bullet speed. Several things going on in that one. They gave you a mass, but the mass was in grams, so you need it in kilograms to do use the formulas. Okay? They gave you kinetic energy, which usually you don't know, and ask you to find the velocity. So you have to use the formula that relates kinetic energy, mass, and velocity, and that, of course, is your kinetic energy is 1/2 mv squared. Okay? Then you decide whether you want to plug the numbers in first and then solve for the v, or solve for the v and then plug the numbers in. We did the second one because it was a little bit less writing. And multiply both sides by 2 to wipe out the 1/2. So you got 2 e sub k is equal to mv squared. Then divide both sides by m. That gives you v squared is equal to 2 e sub k divided by m. And then take a square root to get v. And that's what we did. And when you do all that, you end up with 342 meters per second. And the units play along nicely. Does that answer what you needed?
Yes, sir.
Okay. Any others? All right. 15? Okay. Let's clear the, all right to clear? Sound like an operating room. Clear? Okay. There we clear. Okay. Never mind. 15. Same page, same section. All right. 15. Water is pumped at, all right, here's Haley. All right. I'm required to say this, so I'll say it one more time. Somewhere here. Yeah, here it is. The Vice President for Instructional Services said that we're supposed to call roll from the official class rolls this week. That means only paid students. I believe all 4 of you are paid, so that's not an issue. But it says, if any of the students are not on the official roll, meaning on the paid roll list, please ask them to visit the business office or financial aid office to check on their financial obligations. Make sure things are moving along on that. And it says here we should not allow the student to come back to class until the name appears on the official roll. But I think all of you are already on there, so it's not an issue, but I was required to read this. Now, the only other issue was next Tuesday I have a doctor's appointment in Birmingham, and that's going to be at 9 o'clock in the morning. So there's no way I'm not going to be out of that and back here on campus well before class time. I missed my first class, but I did have to adjust my first class because I'm not there, going to be able to be there at 8:30. We're going to meet at 11. So I'll be in class. Normally my office hours start at 10:45 and go to 4:30. Well, Tuesday, I will teach that class from 11 to 2:15. I believe that's right. No, 1:15. 11 to 1:15. And so I won't be in office hours from 10:45 until 1:15. But after 1:15, I will. Now let me go on and make this other one, okay? I've been hauling around with me for weeks now my evaluations of my instructors, okay? And trying to get signatures, trying to get everything completed on them. I have one instructor who's missing one bit of information, but all the other evaluations are completed except for the signatures. Now, I've got several signatures already, but even after I get signatures, then I got to make copies. And since my printer hasn't worked until today, finally the part came in, so my printer is working again, but I've been having to print these and print everything in various places, so it's just been a long, arduous process. But right now, I'm on the getting the signatures process. I went over to the Birmingham West campus before this class, trying to get signatures. I got one signature. I found out, I had heard something about it. The B building flooded with the last big rain they had. There was one part of the roof, I guess, was weak or something, and the rain came so hard it couldn't run off, or the drain clogged or something. The roof caved in. and at least 2 of my instructors, my office as well, but I didn't even get to go into that, offices were just wiped out. So they've got fans blowing in them and all that kind of stuff now. So I guess they must have gone home to work from home because they couldn't get in their office. I don't know. But anyway, I tried to get signatures today. I got 1 out of 4 I was trying to get today. And I only got 1 out of 4 done. So I'll be on most Tuesdays and Thursdays from now on in the afternoons. I may not be on Bessemer. I may be over on the Birmingham West Campus. So if you can't get me on Bessemer, I may be over on Birmingham West Campus trying to get signatures. So as soon as I get that done, then I'll be working on fall schedule again. So there's always something. All right, we're starting to do 15 on page 218 in section 8.3 problems. Problems 8.3. Number 15. Water is pumped at 250 cubic meters per minute. 250. Now they didn't put a bar. Yes, they did. Okay. This is cubic meters per minute. Yeah. Okay. Now, what that is volume per time. And since we don't have a unit for that or a symbol for that, that's just volume per time. Capital V is volume, little v is velocity, and minutes is in time. However, minutes are not our normal SI unit for time. So I'm going, again, just like I did on the last one, move that to the other side and call this V over T right there. Okay? What is our normal unit for time? The SI unit for time. Not minutes, but we've been using it all term. Seconds, exactly. So this conversion, all we're doing, the 2 blanks in the middle are for our conversion unit, and the first blank's for numbers, the second blank for unit. We always put the units in their place, so what unit goes where? Meters cubed is not involved. It shows up on both sides, so that's not being converted. What are we converting? Seconds, minutes to seconds. So which one goes on top, which goes on bottom? Yeah, second on bottom, minutes on top. Now we match the numbers with the unit. How many minutes in a second or how many seconds in a minute? 60 seconds. Match the numbers with it is 1 minute. You got it. So we need to make this conversion. I'll do the easy part and wipe out the zeros. And that will be 6 into 25 will be 4.11, no, 17. I'm going to keep 1 extra digit there. So I'm going to make it 167. That's more digits than we need, but we'll use them later. 167. I think that's right. Someone do that. 25 divided by 6. Is that what you get? 25 divided by 6. So 250 divided by 60. I don't care, whichever you do. 4.166666. Exactly. So I rounded one of those 6s up to 7. Okay. We only need 3 significant digits. I'm going to hang around with 4 of them until I need to fix it. Okay. Now that's from a lake into a tank that is 65 meters above the lake. So here's the lake level here. Here's the tank up here. And here's the pump down here pumping the water into the tank. Well, this difference here of height is 65 meters. Okay. The A part of this problem asks for what power in kilowatts must be delivered by the pump. So we're looking for power. That's the unknown here. Okay? Now, there's a few other things that we're going to have to fiddle with here. And I'm a little surprised that they're doing this to you. Okay? But they are. Okay? What they're requiring from you here, you see, okay, someone tell me what units power are in. They sort of gave it to you. They said in what units? In part A, what power in blank must be delivered by the pump? They told you. Kilowatts. So what is watt? Let's go back to the fundamental one. Watt. What is a watt? Anyone remember? Joule per second. The time rate of doing work. That's a watt. So this is going to be in joules per second, but tell me what a joule is. Anyone remember that one? We just did it a few minutes ago. It's a Newton meter. Okay, yeah, it's going to be kilogram. What is a Newton? Y'all told me that a few minutes ago. That's a kilogram meter per second squared times a meter. So that's what a Newton meter is, a joule. And then this is divided by seconds again. Sorry, I've written over my arrow. Oh, don't do that. Okay. Get that out of there. Okay. Per second. Okay. Now, nowhere, well, I don't want to say nowhere in this problem do we have a volume. But we do have meters squared, not meters cubed. And I'm trying to remember how, see, I know how to do this. I think it's in a chapter that we didn't do, and I'm sorry about that. That's the one that's going to talk about density. Now we're going to get to that in the next chapter as well. The next one we do is in chapter 12, but I imagine they've already introduced this concept, okay? And that's where your kilograms are going to come from. It's from the density of water, okay?
So skip that one.
What's that?
So skip this one.
Yeah, oh, skip this one? Yeah, if you want to just skip this one, because I don't think there'll be one like this on your test.
Because you said some of them, we wouldn't be able to.
Yeah, I think this is one that is, yeah, I could show you how to do it, but it's going to require either the use of density or some other manipulations here. And just for future reference, if you ever do need it, in the back of your book, I think I've told you about this before. This is on the Appendix C, which is a bunch of tables beginning on page 686, 687, and go on. There's weights and measures, okay, and they do US and SI and all sorts of things there. There's conversion tables for lengths, for areas, for masses, and a conversion table for density. And that's the one you would be using here. You have, okay, let me see. They may not have it for water though. And then you got time, speed, force, power. Yeah. On page 689, the table for density, mass and weight density. We did that in the first chapter, didn't we? Or we did not? Okay. We will be doing it at some point. But there you'll see that water has a mass density of, on table 12 on page 689, in the big block at the top of that table, the bigger block, the last liquid listed is water, and that's 1,000 kilograms per cubic meter. That's the mass density of water. And if you multiply that by your 4.167 cubic meters per second, that would be how many kilograms per second. Then from that you can go on and solve your problem. Okay? But since we haven't done that, you can skip that one for this time. Okay? Unless you want me to say, I mean, it's pretty easy to proceed, but if you don't want it, we don't have to. Well, I don't think there'll be one like that on your test. Let me just see. Everything you need here, I think, is given. I don't see any like that on the test, so you'll be okay. So skip this one.
Yes.
Okay. Any others? Okay. All right. So we're in 8.4 now, which is conservation of mechanical energy. And we were getting ready to do example 1. That's where we left off last time. And by the way, tonight we're going to 7, right? And Tuesday we're going to 7. After that we go back to 6:30. Okay. See, in my other class, I'm going to miss one. We're just going to do the whole class right after then the next period of 11 o'clock. So I always try to make them up if it's my fault. Okay. So example 1. A pile driver falls freely from a height of 3.5 meters above a pile. So here's the pile driver, big old heavy pile driver, coming down the chute here, and it hits the pile down here, and it's going to fall 3.50 meters. Okay? Now in the book, in an earlier chapter, chapter 5, they called this S, which was fine. Now they call it H, which is also fine, okay? Whatever you want to call it, it's just a length measurement, okay? Now, the question is, what is its velocity as it hits the pile? So we want to know V final. Let's just call it V final. Up here, it would have velocity of V initial, okay? Now, what is the V initial? Anyone know? That's where it's being released from. It falls freely from a height of 3.5 meters above the pile. That means when you hear that falls, it's sort of like you release it and it falls, right? You're not throwing it from up there. You're just releasing it and it falls, okay? So what is the initial velocity at the point of release? Up at the top. The initial velocity is zero, okay? Because you released it, okay, from rest. So initial velocity is 0. We don't really need that in the problem, but I was just trying to get you used to thinking in those terms, okay? Now, right at the end of the period last time, we came up with a handy-dandy formula that works pretty well with this one to find that final velocity, okay? Does anyone remember that formula? It's the one we were looking at, and you said, is it the one with the square root? I said, no, not for the problem we were working then. That is the one for the problem now. What does that tell you? Flip back one page, the equation in the green box. No, in the green box. On page 219. Bottom of the page. V is it? Yeah, the one with the square root. What is that? Square root of what? 2 GH. Well, here we got the H. Here's the V we're looking for. That's going to be right here. What in the world is G? You got it. So let's get the square root of 2 times 9.80, what units? Meters per second squared. That's a good acceleration. Acceleration due to gravity. Times h, and what's our h? 3.50 meters. Okay? Now, let's multiply first. You don't have to, but it just comes out pretty easy. So I'd say do a calculator. I can't do this one in my head. That's going to be something pretty close to 20 times 3.5. That's going to be close to 70, not quite 70, 68 or so. Someone do it on your calculator. 2 times 9.8 times 3.5. It's what? 8.28? I don't think so. 2 times 9.8 times 3.5. Now you may be taking the square root. Have you already taken the square root? Oh, okay. Yeah. 2 times 9.8 times 3.5. 68 point what? 6. Okay. So that'll be 68.6. Now you could do it all at once. You don't have to break it down like this. But notice the units. That's why I'm doing this. It's meters times meters, which is meters squared per second squared, because 2 doesn't have any units. Now take the square root of that, and that should be something just a little bit more than 8. Is that what you got before? What? 8.28. And that would be, and you take the square root of the units as well, and that would be meters per second, which is a great unit for your velocity, your final velocity. 8.28 meters per second. Let's see how they did. 8.28 meters per second. Way to go. All right. Any questions on that? That's example 1, top of page 220. Can I delete? 1 second. 1 second? Okay. Take your time. Got it? Okay. Okay. And now we're going to pick up, man, why is that messed up like that? There we go. Here we go. We'll do this one from current slide. All right. Here we've got what we're talking about with conservation of mechanical energy with a pendulum. Now, I'm going to fuss at them a little bit here because that's way too big of an angle to do a pendulum. Because part of the deal with coming up with this formula is that you have small angles you're dealing with. Have you ever dealt with a grandfather clock? You don't take the pendulum up there. It goes back and forth, just a very short thing, okay? Just a few inches, not 65 degrees, okay? So, up here at the top, right before you release it because you're going to release it, the velocity is 0. And if the velocity is 0, the kinetic energy is 0, kinetic energy is 1/2 mv squared, okay? So the velocity is 0, kinetic energy is 0. That means all the energy for this thing is in the potential energy, gravitational potential energy. Now, what's going to happen when you release it, it's going to come down here somewhere. Now, I wish they'd have drawn this line up here to be about the same thing so that we get here. Whatever the lowest point where it's going to go, that's going to be your 0 reference level. So what you're going to have to do is measure the height above that 0 reference level that the pendulum is there. And then mgh, the mass of the pendulum, times the acceleration due to gravity, times your height, this height above the 0 reference level, that's going to be your potential energy. Just like we did with the pile driver, okay? Now, next slide shows it's fallen halfway, and you just have to take the word for it. It's fallen halfway from where it was. The original height was this much. Now it's exactly half that height. Well, now, since it's half the height, its potential energy is half. That means the kinetic energy is the other half, because the mechanical energy, total mechanical energy, can't be lost. It has to be conserved. So therefore, now half of the energy is potential and half is kinetic. And guess where it's going to go next? Right down there. And at this point, it's as low as it can go. And since that's at the 0 reference level, then the potential energy is 0 there. That means all the energy is in kinetic energy. So that's the fastest the pendulum will be going. Now, where will it go after that? It swings on over here. What's it doing now? It's losing kinetic energy, gaining potential energy back. And then it swings on up, and it'll go right up to this level, but then stop, because it can't have more energy here than it had there. And here it has no more kinetic, because that's where it stops, and therefore all the energy is potential, and it's right back at that level again. As soon as it stops, then it starts going down again, changing from potential to kinetic until it's all kinetic, and then kinetic to potential until it's all potential, and then goes back and forth and back and forth and back and forth. Does that make sense? And the kinetic and potential energies are playing seesaw. Okay, they're going up and down. When one goes down, the other goes up, and vice versa. So here it's there's the next two shots. It goes back to the halfway place where it's half and half. Then it goes back to the top, and at the top, kinetic goes back to 0, and it's all potential again, because you're at the same level you were before. It can't go any higher than it was before, because you released it from rest. Now, the only way you could get it to go higher, if rather than releasing from rest, you pushed it. That meant you gave it an initial velocity, so it'll still have that velocity over there, and it'll keep going up. That's what happens when you push kids in the swing. If you push them, they'll go higher. But if you just let them swing, they go basically the same height, but you know there's always a little bit of friction loss, and after a while, they'll stop and say, "Push me again, Granny." Okay, right, or whatever. Okay? So, that's the story of a pendulum. It's just a story of mechanical energy being conserved. Okay? Now, example 2 here is an enormous amount of time. Okay? And they don't have a figure for it. They have a figure for that.
But are we going to have it on the test?
Okay. You may have something like it, but you're not going to have to fill out a table this big. You want to fill out a little bit of it, or just read it and understand what it's talking about? Okay, you're going to do that, or you want me to do that?
I really wouldn't know what it was absolutely talking about.
Okay.
I
Well,
think you explained.
let's go then. Can I go and lose this slide?
Yes.
Okay. And we'll go back to this one and go to the current slide again. I got to get my pen back. Where did my little pen go? There it is. All right. Now here's what the deal is. You got a 5.000, 4 significant digits there, kilogram mass. You're going to drop from a hot air balloon 400 meters, again, 0.0, 4 significant digits above the ground. And they want you to find its kinetic energy, its potential energy, and the sum of the kinetic and potential energy, which we call what? What's the sum of kinetic and potential? Go back one page to 219, top of the page. The sum in the blue block there, the sum of kinetic energy and potential energy in a system is constant, and that's called the mechanical energy. The sum of potential and kinetic. Okay? So when they say total, they mean total mechanical. Okay. Now, so we're going to find the kinetic energy, potential energy, the sum of kinetic and potential energy, that's the total or mechanical energy, in 1 second intervals until it hits the ground. And it's 400 meters above the ground. That's going to be a lot of entries. In fact, you see the table there. So let's start by filling up what we can. We're not going to do the whole table, but we'll start. So first we have time in seconds, and this is going to go 0 to something. 1 second interval. 0.000 seconds, 1.000 second, 2.000 second, 3 and so on and so on. We're not going to do that many, but it keeps on going until it hits the ground. Okay? Now, the distance that it falls, they've been calling h, now they go back to calling it s. Okay? I don't really like s because you confuse it with seconds, but the s is measured in meters. You could call this h in meters, either one. Okay? That's going to be your second column, and we're going to calculate that one. Then the third column is going to be your velocity, and that's measured in meters per second. So we'll come around to that. And then we'll measure E sub k, okay? And that's going to be measured in joules. And then we'll do E sub p, and that's also measured in joules. And finally, we'll do total, which I'm going to call E sub m for mechanical energy, and that's going to be also measured in joules. Mechanical energy is the sum of potential and kinetic. So just to remind ourselves of that. All right. Now, we're going to use a lot of different formulas over and over again. Okay? Now, you'd have to go back to chapter 5, and y'all remember that well, don't you? When you had, trying to think how we named it there. I believe they called it S. So let's keep it S. S is equal to S0 plus V0t plus 1/2 AT squared. I don't know if you remember that formula or not. I guess I need a picture in here too. S0 plus V0t plus 1/2 AT squared. Now I'm going to fix that a little bit for you. S0 plus S0 F V0t, I can't talk, I can't write, minus 1/2 GT squared, because your acceleration due to gravity is always downhill, always negative. So that's the better one to use. Okay? Now, let me draw you a little picture here. Here's the ground, that it's going to hit the ground, but it's starting off that you dropped a 5 kilogram mass from a hot air balloon 400 meters above the ground. So here's the balloon basket, and here's the hot air balloon here. Pretty ugly balloon. And you're dropping the mass of 5.000 kilogram from a height of 400 meters, 400.0 meters above the ground. That's your picture, okay? So at 0 second, what's your height? 0 second, this t is equal to 0, so both of these terms go away. So it's your 400. That's your S0. S0, your initial height. So that's 400.0 meters. Okay? And that's what they got. Oh, no. No. They're saying S is how far it fell. So it hasn't fallen. That's right when you drop it. So sorry about that. This is 0 meters. Okay? And for some reason they just do, it's 0.000 meters. It hasn't fallen any distance at all. Okay? Now, since they're doing it that way, that's going to be your S0 is going to be 0. I was doing S0 equaling 400, but no, they're doing S0 being 0. Okay? And we're going to use this formula up here then, how far it fell. So everything's going downhill. Initial velocity at that point was 0.000 meters per second. Okay? Your kinetic energy, if the velocity was 0, what's kinetic energy? What's the formula for kinetic energy? Okay, it's 0. The formula is 1/2 mv squared. And since v is 0, 0.00 joules. What's your potential energy up there? Now that's where you use your 400. This is your 0 reference level. Down here, the ground, that's where it's going to stop. So, when you're up here, the formula for E sub P is mgh. Okay? The formula for S is the one I wrote, I'll do it again, V0t plus 1/2 gt squared. Okay? The V here, it's change of S per change of time. Okay? We'll come back and get what that is in a minute. And this is kinetic energy, 1/2 mv squared. Okay? Potential energy is that one. And mechanical energy is E sub k plus E sub p. Pretty easy to do. Okay? So, when it's up here, it hasn't dropped any distance, hasn't gotten any velocity, and actually I'm going to use a different formula here. Okay? The formula I'm going to use for velocity here is going to be, and this is from the earlier chapter, chapter 5, this is going to be AT, where A is acceleration due to gravity, so GT. That's going to be your velocity. Okay. Now, I think we've got them all. So what's your potential? Oh, we didn't do potential energy. It's your mass, which is 5.00 kilograms. So let's do this. Potential energy. E sub P is equal to mgh. The mass was 5.000 kilograms times G, 9.80, guess we only got 3 digits there, meters per second squared, times your height. Well, that height is 400 meters, right as you drop it, okay? Sorry, I ran out of room there. So if you got your calculator, 400 times 5 is 2,000, times 9.8 will be 19.6. 19600 joules. And they should have, yeah, 19.6. And they have a bar over that because they say that's the 4 significant digits. Now what's messing up here, the G only has 3 significant digits, so they shouldn't be carrying around 4, but it's okay. We'll let them get by with it. And then what's your mechanical energy? Kinetic plus potential. So that's 19.600 joules. Okay? All right. Isn't this fun? All right.
Multiplied the 5 and 9.8, right, and got 19,600.
Okay. You also have the 400 there. I had to write that up to the thing. 400. That was the height. MGH.
Okay, so I multiplied 400 too, right?
Yeah. 5 times 9.8 times 400.
That's 7840.
Say again?
I got
Okay, let's do it again. 5 times 9.8 times 400. 5 times 9.8.
oh, just 5.
5 times 9.8 times 400.
Okay.
Got it?
Yes.
19,600 joules. It says your kinetic energy was 0 right when you released it. All your energy was potential energy, so 0 plus 19.6 is 19.6. Okay. 19,600. Now, 1 second later, 1 second after you dropped it, your V0 is 0, so this isn't going to do anything. It's 1/2 GT squared. Okay? 1/2 of 9.8 is 4.9, right? And then multiply that by 1 squared, and you get 4.900 meters. They just put 4.9. I don't know why, but they're putting 4 digits everywhere else, but they're not putting it there. Now, what's the velocity? That's your 9.8 times 1, so that's going to be 9.800 meters per second. Your G times your T. All right, now you've got a kinetic energy because you have a velocity. So it's 1/2 the mass, which is 5, times the velocity, 9.8 squared. So someone do that. 1/2 or 0.5 times your mass, or what you can do, since the mass is 5.000, 1/2 of that is 2.500. So 2.5 times 9.8 squared. What do you get? (2.5) times 9.8 squared.
5.33.
Whoa, no. Okay, try it one more time. 2.5 times 9.8 squared.
240.1.
Okay, and for some reason they rounded, it's 240.1, and that would be joules. Okay? You want me to come watch you plug in, or did you get it?
You can watch me plug it in.
Huh?
I can come up there and plug it in.
Oh, no, I don't mind. I need to get up and move some. I hate sitting too long. Y'all have to sit. I don't have to. I get to move around. Okay.
You said 2.5.
2.5 times, see, which one are we doing now? Oh, yeah, 2.5 times 9.8 squared. And then the squared heat is, that's the square root of heat. That's heat. To the 40.1. And that would be joules. Okay? Now, your MGH, okay, if you have fallen 4.9 meters, you subtract that from the 400 that you were, so that means your height is now, and they probably should have put this column in there too, 395.1, because you were at 400 and you have fallen 4.9. So that would give you 395.1 meters. So that's your height now. Oops, meters. Okay? That's ugly. All right, let's get that corrected. Okay. So now what you enter for your E sub P is 5, that's your mass, times 9.8 times 395.1. 5 times, where am I again? 9.8 times 395.1. MGH. Say again? 19? 59 joules. Okay. Now, what I want you to do is add that one to that one. Yeah, round it off, make it 60. Okay. And add 240 to 360, and you get 600. So it's 19,600 joules. Okay? And you see your mechanical energy is conserved. You don't lose it. Your kinetic is increasing, but your potential is decreasing by the same amount. Okay. You see how to step through the table then? Yes. Okay. You need any more?
No, sir.
Okay.
I'll continue to listen once I get home.
Okay. Good deal. All right. The one thing that they are a little fuzzy about, the S over here, I said this is either H or S. The S is how far you've fallen, okay? And the H here, so I'm going to take off the H here. The H here is from the ground. How far you are above the ground, okay? So the S on the second column, the one that you use there, when you do, that's what you're calculating. It's 1/2 GT squared, okay, from whatever time you had. That's how far you've fallen from the top. And the difference of that and where you started, that's your H over on the fifth column, or yeah, whatever that is. So you have to subtract your S that you calculate in column 2 from your 400 to get your H that you use in column 5. That's the one place they were a little, and they say it, if you read the part under example 2, it says in column 5 use H equal 400 meters minus S, okay? And so that's what you use. All right, now, okay with that?
Yes, sir.
Okay, so let's escape this and discard it. and we're going back to our other one, which is here. And we'll go from current slide right now, but we'll advance it one. And here is your roller coaster. Okay? If you've ever figured out how these things work, and if you've ever really noticed, the roller coaster starts at a really high level. One of two things are happening. If they start you down here, then they have to pull you up to there. Okay, they have a chain or something under there that's pulling you up to there. But once you get to the top, the P up there, then they let you go. And as you go, you're going to see what they've done. As they pulled you up there, they increased your potential energy. So there you're at your maximum potential energy, but you're at zero kinetic energy. And once you start coming down, you're gaining kinetic energy, meaning you're gaining speed like crazy, and you're losing potential energy. And you come back down here and you're going as fast as you're ever going to go, right there, okay? And then you start going back up again, and that's where you lose your kinetic energy and start gaining potential back. But notice you don't get as high as you went there, so you still got some velocity here, and you go to all these other things. It gets back here, and it will, if they let it run, it would get you right back there. It really wouldn't, because there's always a little bit of friction loss on the track. The fact that you can hear it when it goes over the track, if that was perfectly silent, there wouldn't be any friction. It's never perfect. It's going, but I'm not talking about the people screaming. I'm talking about the wheels on the track. There's always some friction loss. But your reference level is as low as you can go, and then your highest part there, that's going to be your maximum potential energy, and the lowest part is going to be your maximum kinetic energy. Okay. Now, they talk a little bit about elastic collisions here. And just so you'll know what they're talking about, oh, that's something else. And an elastic, what do you think elastic means? Okay, we think of it meaning stretching. What it actually means is what happens after the stretch. An elastic collision always returns to its original shape. That's why the elastic, you want it to come back to its original shape. If it doesn't, then it's no longer elastic. It's now what they call plastic. So an elastic collision, after the things collide, they go back to their original shape. Now you might say, but no, it never did lose their shape. Well, yes, they did. Have you ever seen a slow motion shot, and you just name your sport, a tennis racket hitting a tennis ball? If you look at a slow motion shot of that, that ball actually flattens out like crazy, and the racket bulges in the back, and then immediately sends the ball flying in the other direction. The racket goes back to its original shape, the ball goes back to its original shape. That's an elastic collision. Believe it or not, a baseball hit by a baseball bat, you know, a baseball bat is rounded like this, and the baseball is a hard old ball, right? Okay? When you see it hit, especially some of these real sluggers that can hit it so hard, Bo Jackson, you know, people like that, that ball actually folds around the bat just ever so slightly, instantaneously, but then goes back to its original shape. The bat actually flattens out a little bit. You can't see it happen there, but it does a little bit. A golf ball, a golf club hitting a golf ball. When they swing that thing, especially those hard hitters, the ball, that hard little golf ball, how hard that thing is, it actually does flatten out against the head. And the head doesn't distort, but it bends backward. The shaft bends backward, and then it slings it on out there. The ball returns to its, that's an elastic collision. What elastic means, it returns to the original shape. Okay? And in elastic collisions, the total kinetic energy of the system before the collision equals the total kinetic energy after the collision. Most collisions are not elastic. If you think about a collision on the highway, Does that fender go back to its original shape? No, it's crinkled. So you lose. That is not an elastic collision, okay? So you do not return. But if it was a perfectly elastic collision, then the total kinetic energy before the collision equals the total kinetic energy afterwards. That's the only reason they mention it here. They don't do anything with it except mention it. There's no problems that they work on. Now, the little blurb here at the bottom of page 223, at the top of 223 is you step firmly on a red ball so it will not move. When you strike it with a croquet mallet, the green ball is going to take off and go. Because all the energy that you use to hit the red ball, even though the red ball doesn't go a thing, it's an elastic collision, so that transmits the kinetic energy to the green ball and it takes off. I don't play croquet, but I used to when I was a very young child. Okay, landing on an aircraft carrier, the pictures on the next page, they have, because that's a very short landing strip, and that's plane is a jet plane going at a very high rate of speed. They have these cabling across there, and you are, that cable is tugging on you backwards. To take off from an aircraft carrier, they have what they call a catapult that throws the plane off the thing. Of course, they've got the engines at full speed, but it throws it off. And I have made one carrier landing and one carrier takeoff. I wasn't flying, I was a passenger, but it is an unusual field. Problems 8.4, do any of the odds 1 through 13. Okay. Yeah, that's on page 224. That's the section we just finished.
1 through.
Say again?
What did you say?
Any of the odds 1 through 13. All right. Now 8.5 is just sort of a talking one. There's no problems we're going to do. There's no examples we do. It's just a little bit of talking. So let's briefly talk about what they're discussing here. They're talking about alternate energy sources. And if you've been hearing much in the news lately, you'll know that we are using more carbon than we ever have before, even though we're supposed to be cutting back. But as a planet, we're using more. Some governments aren't cooperating very well, as in ours. Others are sort of probably cheating, but other new economies are just now beginning to grow. They're using way more than they used to. So the idea is, how can we use other energies rather than fossil fuels? One, and this has been happening for years here, is hydroelectric energy. And that takes the advantage of flowing water to generate electricity. And what they do, they build these big dams, piling the water up behind the dams, and then when the water falls through the dam, it goes at a high rate of speed, it turns a turbine, a water turbine, and that creates electricity. So you don't have to burn any fossil fuels at all.
But they bring a lot of solar panels in now.
Exactly. Okay.
Where we live on the base,
Right.
the whole air strip, everything is just solar panel. And where we live, our house,
Right.
there's a solar panel over it now.
Fantastic.
They're starting to put them on top of the houses.
Right.
It's out on the fort.
Fantastic. And that's Fort McPherson or
Fort Rucker.
Fort Rucker? Okay. Oh yeah, you're down, way down. Right. Okay.
So they starting to use more and more of those, and they say in the next couple of years, pretty much it'll be basically all solar down there.
Yeah.
That's what they were saying, but it's not going to happen.
Well, they'll use any they take off the grid. That's good. The thing is, solar at night it doesn't produce. You have to have it stored in batteries, and on cloudy days it doesn't produce as much. But If they combine that with wind, then you can pretty much cover a lot more. And then if we just supplemented that with hydroelectric, the trouble about hydroelectric is dams are very expensive to build. They take a long time. And you flood a lot of land, but behind the dam, a lot of land is flooded, and people don't like to lose their land. So we did this back in the, probably the teens and 20s, 30s maybe, even into the 40s, maybe the 50s. But since then, they've not been building very many hydroelectric plants. Alabama probably has as many as any state for its size. There's Smith Lake Dam, Gunnersville Dam. There's just all over the state. You'll see all these hydroelectric plants. But that's in the northern part of the state. When you get down south where it's real flat, if you built a dam there, it would flood just huge acres of land. That's good farmland down there. They can afford to flood it, and people live on it too. So most of the good sites for building dams have already been built, and there's just not that many other places to do it. But hydroelectric, it's a great source of energy. It's costly in that you have to build the dams, but when it's built, it's not that costly to operate. Okay? The second one mentioned here is wind energy, and they show several pictures of these wind farms. And they're beginning to do more of these now, not so much in Alabama yet, but we're going to get there. But out west, my wife had meetings in Salt Lake City, or near Salt Lake City, a couple of summers ago, and it was just the weekend between, terms for me, so I got to go with her. So we left a few days early and drove around. We went to Yellowstone, but it was so crowded we couldn't see anything. We had been there before. We drove through Teton, and we just decided to drive through parts of Montana and Idaho and Wyoming, just real close in the area there. And we just passed so many wind farms. And what more, they had the big turbines there, but now these are in a desert, it looks like, so nothing going on there. But underneath the wind farms, the farmers were down there baling hay. So there's nothing to keep them from baling hay underneath the wind farms. So they had rented out their land, but they were still using their land. So there's the wind energy. Geothermal energy. Now I mentioned Yellowstone. Yellowstone is one place that has a lot of that, but there's other places too. The West Coast has more than we do because we don't have any volcanoes in the area, thank goodness. But if you can use the energy that's inside the earth, like Old Faithful, every hour is making enough steam to send up a plume of water. And then the solar energy in the picture on page 226 is a picture of a garage with solar panels all over that roof, right? And that's what you got at Rucker, right? All right. So that's basically it. The potential for alternative energy replacing or reducing our dependence on fossil fuels is promising. But the U.S. alone needs 5 times more energy than it can produce through fossil fuel production. So that's a lot of energy. We're just getting started on it. But it's good we're doing it. All right. That's the end of the chapter. There is a glossary. There's wind turbine technician. That, I don't know. You can read that if you'd like. It's interesting. Wind energy, the physics in action there. The glossary's there with some definitions. The formulas, those 4 formulas we've used a lot in this chapter. Don't worry about the one with the cosine in it. You won't need that. The review questions are really conceptual, multiple choice most of them, but you can think through those. The review problems, these are much more like what you did at the end of each section, so any of the odds there would be fair game. Okay. And then the last little slide here is another roller coaster deal. Okay. This time you're starting off at 60 meters up. Okay. And what they're asking you to do is applying the concept here to calculate if you had no friction loss, what would be your velocity at all these other points. Okay? With the 60 meters, that would give you the h. Okay? And then using the velocity equal the square root of 2gh, you can calculate when you're at 20 meters, when you're at 30 meters, when you're at 40 meters, and you can calculate down here when you're at 0 meters. That would give you your velocity at every one of those. What you do is the difference in h. So 60 minus 20, that would be 40. 60 minus 60, that would be your 0 there. So. Yeah. So anyway, that's your that problem there. There's nothing that you have to do, but it's pretty interesting. Am I ever going to get on a roller coaster like that? I don't think so. Okay, that's not my bag. All right. Now that finishes chapter 8. So before I forget about it, let me go on and give you the test for chapter 8. Now, I don't know if all of you have turned in the chapter 6 test yet. Have you?
It's right here.
Okay.
I
Are you ready?
it to you.
Still working on it?
No.
Oh, okay, good. The rest of it, I think, have. So I'm not even making one for that other person because she's never been here. I don't think she's going to come. It's a bit late to be coming. So let me put this here and put this back in this place. If I don't, I'll forever lose it and get really confused. Okay. All right. Now, technically, due next Thursday, but if you need more time, you certainly can have it. Okay? Just don't still have it when we go finish chapter 12 and you get another test. So that's where we're going next, is chapter 12. Skipping not, which is rotational motion. Don't think you'll need that in anything you do. Chapter 10, simple machines. Don't think you'll need that. And chapter 11, universal gravitational and satellite motion. I don't think you'll need that. But they did say you would need matter, because it matters. Okay. If you go back to your, course description on the syllabus, you'll see they did say, I can't remember how they phrased it, but something about the forms of matter. So that's going to be chapter 12. Okay? So that's the end of the slideshow. Let's close this one out and come back to this one and pick up. Ooh! That is totally bizarre. Ah. No. Something's really strange here. Why are they out of order? I don't know. These are from the bottom up, so we're now in chapter 12. Okay. And we'll start with the current slide. How we're doing on time. Oh my goodness. Okay, oh, we're almost, well, we got only about 20 minutes to go. Wow, time has flown by tonight, or for me it has. Maybe for y'all it's drugged, but for me it's been pretty fast. Okay, chapter 12 is talking about matter. Okay? Now, there's a few words they want to deal with first, so actually I'm going to back up here. I'm going to write them on here. Okay? I like to indicate, especially when they do the bold letters, okay? Bold words. First, matter is anything that occupies space and has mass. Let me get my pen back. Okay. Anything that occupies space and has mass. Okay? Now we're going to deal in several types of approaches to matter. Okay? The first one of these, what we're going to do right now at the very beginning, is talk about matter in the most elemental way you can. And there's going to be two areas. I'm going to call these the macroscopic and the microscopic. Okay? My writing stinks, but that's what it's. Now, the book doesn't use these terms, but I found they're sort of useful. Okay? The macroscopic thing, we're going to talk about the concept of elements. Okay? What an element is a substance that cannot be separated into simpler substances. Cannot be separated into simpler substances. Okay? Now, what that means, let's just say the metal in this chair. I don't know what kind of metal it is. My guess is probably steel. Steel is made up mostly of iron. Iron is an element. You can break iron into smaller and smaller and smaller and smaller and smaller and smaller pieces, but at some point, the smallest piece you got of iron is going to be an atom of iron. Oh, and by the way, did you know we were going to 7 tonight?
Yeah, I was putting it.
Okay. Iron is the smallest piece. When you get down to the smallest piece of iron, that would be an atom of iron. Now that is incredibly small. You'll never see an atom in your life. You might see some pictures of things that look like that's where an atom was or something like that, but you'll never actually see an atom. It's just too tiny. Okay? So, on the macroscopic scale, an element cannot be separated in simpler substances. So on the microscopic scale, you have atoms. Okay? And all the same kind of atoms that makes up what we call elements. Okay? Now, if it's something that can be broken into 2 or more elements, that's called a compound. 2 or more elements. Now I want to add another phrase to this. The book doesn't say it, but I'm going to say it. Combined chemically. Combined chemically. Okay? Now that is kind of an important concept here, but we don't really have time to go into it. But let me just give you a couple of examples. Does anyone know what sodium is? You've probably never seen any sodium in your life. Okay, you almost definitely have never touched any sodium in your life. Because sodium is, actually they call it a very soft metal. Now that sounds contradictory, a soft metal, but it is. A very soft metal. I think it tends to be a little yellowish in color. But if you've ever seen any, it's probably been in a beaker that's been covered with oil. The sodium is that stuff at the bottom, and the oil is on top. And the reason for that, if sodium, pure sodium, an element, sodium, ever touches a water molecule, we'll get on what a molecule is later, there's going to be a major explosion. Okay? Sodium reacts violently with water. So that's why I say you've never touched it. If you had ever touched sodium, you just burned your hand really badly because it's going to suck the water right out of your tissue and make it burn like crazy, because it gets very, very hot. It's a violent reaction. So sodium is a soft, very reactive metal. Okay? Anyone know what chlorine is? What? Chlorine. Now you probably are thinking Clorox.
It's like the chlorine that they put in the pools.
Okay, now, okay. That's more like Clorox, okay? It is, they call it chlorine, but it's more like Clorox. It's got chlorine in it. What chlorine actually is a green, poisonous gas, okay? You'll sometimes see these tanker cars go by, and they'll say hazardous, and they'll have, and if they ever turn over and leaking chlorine gas, everybody leaves the area. They evacuate everybody because it's a green, poisonous gas. So here's sodium, a soft, sort of pale yellowish metal that's an incredibly reactive metal, and a poisonous gas, green gas. Okay, that's what they are as elements. When they combine chemically, what do you have? I think you just ate some. What did you have in your bag?
Oh, these seashells.
Oh, okay, let me see. Can I see? I won't touch it.
Sunflowers.
No.
Sulfate.
Okay, what's number 2 ingredient?
Sunflower butter.
Right before butter. Number 2 ingredient. Sunflower seeds.
Sunflower seeds. Salt.
Salt! You just ate some sodium chloride because you ate salt. We put it on our food all the time, don't we? It's a white crystal. It doesn't look like a soft green metal.
You know what? You sure is, because they said watch your sodium intake, which is salt.
Yeah, which is salt, exactly. Now, but they mean sodium ions there, okay? And we'll get to that a little bit later. But sodium, see, salt, NaCl, is a compound that's made up of 2 or more atoms, different atoms, okay? But when they combine together, their chemical characteristics change completely. Because how could you be eating something that would sodium? No, you're not eating sodium. There's sodium in it, but that sodium is no longer a soft, yellow, very reactive metal, and that chlorine is no longer a green, poisonous gas. When they combine together, they form a crystal of sodium chloride, which you use to put on your food, and you eat it. You watch your sodium intake, but that's it. So a compound is 2 or more elements combined chemically, meaning they've changed completely from what they were. Another example. Anyone know what hydrogen is? It's a gas. It's the lightest gas there is. And it's also very explosive. Have you ever heard of the Hindenburg? One of the early blimps, because it was a lighter than aircraft, they put the lightest gas available, which is hydrogen, filled it up, and it floated really, really well, and you could carry around a bunch of people in the little car underneath. But there was, they think either there was a thunderstorm happening, either it got struck by lightning, or it ran into something and enough friction tore it and created enough heat, it blew up. I mean, it was a...
It was the air balloon, wasn't it?
Yes, exactly. See, hydrogen is a very flammable gas. Okay? Now, what is oxygen?
Oxygen is air.
Okay, oxygen is also a gas. It is in air. In fact, about 20% of the air in the room is probably oxygen. 18 to 20%, something like that. It's necessary for us to live because that's what we oxidize our food. We burn our food. That's why we have a temperature of 98.6. The room temperature is 70 degrees. We're at 98.6. We're oxidizing all the time. We're burning carbohydrates. Okay? So oxygen is the element that's necessary for combustion to happen. So here we have hydrogen, which is a very explosive gas. It burns like crazy. Oxygen, which is the element that's necessary for any combustion to occur. And yet, what happens when we combine them chemically? H2O. What is that? H2O? Water. You've got some in your thing right there. You've just been drinking an explosive gas and a flammable gas. No, they're not that anymore. They combine chemically and form liquid water, which we use to put out fires. Isn't that strange? An explosive gas, the one gas that's necessary for combustion to occur, when they combine chemically, they become a liquid that you use to put out fires. Okay, really, really bizarre. Compounds are two or more elements combined chemically. Okay, now what is a compound made up of? Compounds are made up of molecules. On the microscopic scale, compounds are made up of molecules. Okay? Now, elements made up of molecules also, but all of them have the same kind of atoms. Compounds made up of molecules made up of different atoms. Okay? And that's where the next picture comes into play. Okay? Here's the one I just talked about. An explosive gas, hydrogen, that's the blue balls. And the big green ball is an oxygen atom. And believe it or not, this is how they combine. They never combine opposite each other, always at an angle. And that makes a water molecule. The water molecule, water being a compound made up of two different types of atoms, is composed of two hydrogen atoms, one oxygen atom, and we express that chemically as H2O. So if you ever see H2O, they're talking about water. Now this is a lot more complicated, but this is what was number 3 ingredient there on your bag. Okay, next.
Buttermilk.
Next.
Cheddar cheese.
Oh, wow.
Milk.
Is sugar anywhere on the list? There may not be any sugar in it. Sorry, I thought maybe there was a little bit of sugar in it. This is a sugar molecule. Now in this one, the red balls are the carbons, the blue balls are hydrogen, just like they were before, and the green balls are oxygen. Now this time they didn't make the green balls that much bigger than the blue, but this is what it's made out of. And by the way, sugar is called a carbohydrate. Carbo from carbon, hydro from hydrogen. The ATE, that means it has oxygens in it. In fact, it has lots of oxygens in it, okay? Well, it has more hydrogen, okay? So here's what this is a glucose molecule, okay? It has 1, 2, 3, 4, 5, 6 carbons, so it's C6. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens, H12, and 1, 2, 3, 4, 5, 6 oxygens, HO6. That's your simplest sugar that you can have, glucose. Now there's some very similar sugars called fructose. It's also the same formula, but some of these bonds are rearranged a little bit. And glucose, fructose, and there's one more, sucrose. Sucrose has the same chemical composition, but they're arranged a little bit differently. Okay? And that makes up. So there is a compound made up of 3 different atoms. And of course, this is very, very different again. Carbon, which pure carbon is basically usually black soot. Okay? That would be your best expression of carbon. Hydrogen, an explosive gas, and oxygen, a gas that supports combustion. You mix them together in this type of arrangement, and you get something that makes food really sweet. Okay? Your cakes, your pies, your candies, things like that. That's your sugar. Okay? Glucose. Fructose, you find, yes?
What is Splenda? What form of sugar is that?
Okay. What they've done, I don't know exactly, but I guess on it. What they've done with Splenda is taken this, or something similar to this, and just made a little bit of a tweaky change. Maybe replaced this with a hydroxyl or something else like that, and just made enough of a change so it still tastes sort of like sugar, but your body doesn't process it like sugar because the chemical composition is a little bit different. I don't know what the change they've made. What do they call it? Sucralose? Is that what the name for it is? One of those sweeteners is sucralose. I think that may be Splenda. They start with sucrose and change it just a little bit. And you get the sweet taste, but you don't get the load on your pancreas because your body doesn't metabolize it. You pass it right on through. Whereas sugars, your body processes it, and your pancreas has to break it down. And when your pancreas gets overworked, pretty much that's sort of what happens with diabetes. Your pancreas sort of starts shutting down. Now, some people, type 1 diabetes, they never worked in the first place. Type 2, you overworked them sometime during your life, and they sort of broke down on you. Okay. So this is what we mean by compounds made up of different atoms or elements. Okay? Now, the word atom actually came from, because it's the smallest particle of an element that can exist in a stable or independent state. The ancient Greek guy named Democritus came up with the concept originally, and he said the very thing I said earlier. If you had a piece of iron and kept breaking it and breaking it and breaking it and breaking it, at some point you get to the smallest piece, you can't break it anymore. So the word atom meant indivisible, which means you can't break it any further. But we know today that atoms are made up of even smaller particles, but these are not particles that can exist by themselves. So that's why they put the word in here, the smallest particle of element that can exist in a stable or independent state. Okay? Now, what is an atom actually made up of? Are we going to have to save that for next time? How are we doing on time?
3 minutes.
Is that 3 minutes? Well, let's see if we got time for this, okay? What an atom is made up of is 2 pieces, 2 parts. There's a part in the center that is incredibly tiny volume-wise, okay? That's called the nucleus. And in the nucleus, you have these 2, you have a few more, but mostly 2 things, protons and neutrons, okay? Now, these are incredibly tiny, but they have a certain amount of mass. Now, around that nucleus, taking up all the volume of that atom, are these electrons. These electrons are floating around there, circulating, around that nucleus. They have almost no mass at all. If you'll notice there, the electrons have 10 to the minus 4, between 10 to the minus 3 and 10 to the minus 4. They're between 1,000th and 1/10,000th of the mass of either a proton or a neutron. Yet that protons and neutrons are packed into a nucleus that is incredibly tiny. The electrons are almost no mass at all, and they're floating around here taking up all the volume. Okay? So it's a rather strange setup. They don't even know what the diameter of an electron is. It's so incredibly tiny, they can't do it. They can measure the diameters of protons and neutrons. And if you'll notice, a proton and a neutron have almost the same mass, basically the same diameter, but they have very different charges. Protons, P, positive charge. Electrons, negative charge. Even though they're incredibly tiny, they have the same charge as a proton, which are 1,000 to 10,000 times more massive, but they have the same charge, only the electron's negative and the proton's positive. Whereas a neutron, no charge at all. So think neutral, okay? Neutral. All right. Now, if you think about this very carefully, if you move this decimal place 1, 2, 3 more places here, then that would be 4 places. 1, 2, 3, 4 places. That would be 10 to the minus 27. And if you added, that's almost a 1 there. See the difference in the masses of the proton and the neutron. Neutron's a little bit more massive. It's almost the same as that of an electron. Okay? Not quite, but pretty close. Just a strange little thing. So the center of every atom is a nucleus. That's where almost all the mass is, surrounded by a huge cloud of electrons, which have almost no mass at all. Strange setup, okay? And we will start at the top of page 312 next time, okay? Any questions? Okay. Be working on your tests. We'll start at the top of.
So we should have grades when we come in Tuesday.
What's that?
We should have our grades by Tuesday or next Thursday.
I hope to get them graded. I know this sounds a little weird, but it depends on if it rains this weekend. If it rains, I can't do as much work outside. I'll probably be able to grade some papers. If it's not raining, and then it also depends on my doctor's visit. I have a feeling I'll be sitting in the waiting room. In fact, I go early. I go an hour early so they can take the blood first, and then I go see the doctor. They have to wait an hour to run all the blood work. So I have an hour to kill there. So I think I will have the paper graded. Okay. By Tuesday. All right, you too. If it rains much this weekend, I may have them graded before I go to the doctor.